Good morning. I would like to present the publication, Hall Effect Diameter Sensor Integration in DIY Filament Extruder. The rapid increase of 3D printing popularity in public knowledge in the last decade is largely the result of the Stratasys patent expiration in 2005. Additive manufacturing, not only FDM, have their advantages, despite there are many solutions on the market that are far superior in terms of speed, strength and visual properties. They are noticed more frequently by both the scientific community and manufacturers in the last 5 years. But parallel to the professional community, there is also a makers community gathered around projects like RepRap. With extremely low entry cost, still dropping prices of consumer-level 3D printers and wide range of cheap consumables, FDM Technology is a way to go for many talented young people with ideas. One of them is creation of do-it-yourself filament extruder to recycle waste materials, supports, failed prints, etc. into the new spool of filament. While filament production line price starts at around €50, and desktop-style filament extruder, like 3Dvo's Precision and Composer, can cost almost €70, the idea of creating a similar, in terms of functionality, machine in €100–200 range is quite encouraging. The filament extruder is a simple design based on a cylinder barrel with a screw inside. The material in the form of granules or flakes is placed inside hopper, from where the screw driven by a high-torque electric motor directs it towards the heating zones. The zones are heated by independent heaters, with the possibility of independent control of their temperature. The melted material is squeezed out through the mouthpiece of the nozzle and cooled. In the case of a built device, the material is cooled by air. The key element of the device is the screw. It is responsible for feeding the material from hopper into the melting zones, increasing the pressure of material and mixing it. Thanks to their design, proper screw feeders are better able to build stable pressure in front of the mouthpiece, which translates into a more stable outflow of material from the nozzle in the case of uneven flow from feeder. Finally, the melted material is formed in the mouthpiece of the nozzle. It is worth noting that the temperature of the nozzle in the filament extruder is definitely lower than in the case of 3D printing. This is due to the much larger diameter of the mouthpiece, corresponding to the dimension of the extruded filament, e.g., 1/75 mm for 1/75 filament. Thanks to this, the material after leaving the nozzle has denser consistency and helps to reduce the impact of extruded swell on filament. Die swell, also known as Barris effect, is a common phenomenon in polymer processing. In the case of a filament extruder, it swells the filament when it leaves the nozzle. This phenomenon is eliminated in industry by using appropriate mouthpieces and calibration devices. The last element of the device is the filament winder. An ordinary DC motor drives the spool, on which the material is wound, through a frictional translator. The use of a friction gear with low pressure allows you to resign from controlling the winding speed and do not impact calibration procedure. The obtained material had an acceptable quality, which made it possible to use it for 3D printing. It should be noted, however, that it differed significantly from commercially available materials. The main reason was the need to ensure constant and consistent flow of the granulated material from hopper to mixing screw barrel. Any changes was triggering fluctuations in the filament diameter, which had to be manually detected and compensated by adjustment of calibrator motor speed. Unfortunately, the simplicity of the entire device has a significant impact on its functionality and usability. The most important of them are manual control of filament dimension, extensive calibration process, no automatic control system for obtained product. The hardship of preparing the device for proper operation is associated with the long-term process of selecting operating parameters. Some of them must be made once, such as the selection of the correct temperatures of the extruder zones for a given material. But the calibrator motor speed should be constantly adjusted during the process to compensate for heterogeneous pressure changes in the extruder. The next step, dictated by the imperfections of the project, was the decision to add a filament diameter sensor, allowing to monitor the process and provide feedback to the control system. Taking into account that the main problem was the obtained filament diameter, and in order to keep the costs of the student project as low as possible, it was decided to implement a simple meter based on a linear Hall sensor and Arduino-compatible board. An open-loop system do not provide any feedback from the output of production process. As a result, there is no possibility to self-correct and adjust the parameters. Human action is necessary to check the process and parameters modification. In opposite, there are closed-loop systems where sensors are used for monitoring and self-correction. At this point, the only available sensors in the constructed extruder were 3 thermistors, used for monitoring and controlling heaters through the controller. Adding additional diameter sensor to the system will enable possibility for monitoring filament dimension and allowing automatic calibrator motor speed adjustment, Figure 5. Since a contact sensor will be used, it is necessary to place it behind the cooling zone to avoid deformation of the filament during the measurement. An open design by Thomas Sandler was used as the basis for the preparation of the sensor. In this project, the filament is routed between 2 bearings, and the change in the distance between them moves the magnet placed on a long lever, changing its distance from Hall linear sensor. A huge advantage of the sensor design is the minimal pressure of the upper bearing on the filament, caused by counterbalancing bearing weight by the magnet mounted at the second end of the lever. Second benefit of placing magnet on lever is multiplying travel distance, which allows to increase readings resolution. The sensor consists of parts made in FDM Technology, a small neodymium magnet, a Hall 49E sensor in the T92 housing, 4 608ZZ bearings, and 3 sections of 8 mm shaft. The sensor measures the strength of the magnetic field of magnet placed on the sensor's arm. The measurement is based on a phenomenon discovered in 1879 by the American physicist Edwin H. Hall. Its principles: the production of a voltage difference across an electrical conductor placed in magnetic field. For this to happen, conductor must be simultaneously in a magnetic field with a transverse flow in relation to the position of the element. A specific voltage is then created between the planes that limit the conductor, which is at the same time perpendicular to the plane determined by the direction of current flow. All this also occurs as a result of Lorentz forces causing the movement of charges in the magnetic field. Thanks to the use of the 49E linear sensor, it is possible not only to detect the magnetic field but also to determine the change in its intensity, which in our case makes it possible to read changes in the diameter of the filament. To avoid complicated mathematical operations and additional strain on the Arduino Nano, the lookup table, LUT, was used to convert the value of the magnetic field strength to a distance in the project code. This solution simplifies the implementation of the whole and allows quick calibration of the sensor. Calibration was performed by placing elements of known diameter or thickness between the sensor measuring bearings to read the value of the raw data for a given measurement. Correlated raw values, measurements of magnetic field, and corresponding values in were then entered into the LUT. The created array allows to quickly verify whether the raw data being checked have their equivalent in the array. In their absence, values can be quickly estimated based on the existing ones. The resulting diameter value is then compared with the expected 1.75 mm, the most commonly used filament diameter in FDM devices, assuming an accuracy of plus or minus 0.02 mm. If the result is within the tolerance range, Arduino sends only information about the current filament diameter through the serial port to controller. In other cases, commands are also sent to gradually increase or decrease calibrator motor speed for too large or too small filament diameter, respectively. The scheme of the program is presented on the slide. Multiple tests were performed with sensor installed in the extruder assembly. Depending on the accuracy of the initial device settings, typically sensors are allowed to stabilize the filament diameter in less than 2 minutes and keep it within plus or minus 0.1 mm tolerance throughout the process. The sensor certainly fulfills its function. Its assembly allowed not only to speed up the start of the process but also made it much less absorbing for the user. The feedback loop to the controller accomplishes its function and enables automation of the filament calibration process, and the resulting product is usable. This can be seen especially when comparing the spools with the material prepared before its installation. However, The obtained tolerances plus or minus 0.1 mm do not allow the material to be used for precise FDM prints. It would be optimal to achieve accuracy at the level of plus or minus 0.05 mm. The use of the sensor also did not allow to increase the speed of the entire device. As the speed increased, the filament reaching the sensor was not sufficiently cooled and began to deform. On the other hand, tests with an extended cooling zone significantly decreased the calibration process quality. Not only did the material deform under its own weight, but the increased distance between the nozzle and the sensor drastically amplified the inertia of the entire system. The filament extruder prepared as part of the student project was a great experience for the team in the field of mechanics, control systems and programming, both at the stage of creating the device prototype and during its successive expansion. Comparing the applied solutions to commercial ones, analysis and solving problems brought results and allowed to draw conclusions. The use of a touch sensor did not turn out to be an ideal solution. Although easy and cheap to assemble, it is troubled with some limitations. It would be optimal to place it as close as possible to the nozzle in order to accelerate the reaction to the occurring changes in diameter. However, a contact sensor placed in or even in front of the cooling zone will deform the material. In such a location, it would be optimal to use an on-contact sensor, for example optical. Another idea is to cool the filament with liquid, as is the case in industrial production. The liquid will not only allow for faster cooling of the material, but also thanks to the buoyancy and surface tension, it will allow the cooling zone to be extended. A more efficient and longer cooling zone will allow to accelerate and stabilize the whole process by reducing material hanging in the feeder and more stable pressure building in the mouthpiece zone of the nozzle. Thank you for your attention.